Hello there, and welcome to Two is Better Than One. The title sounds like I'm trying to sell you something, but I'm going to explain what that means. My name is Sankarshanan. The answer to the question, how many syllables can you fit in a single name? I will be your host today, and thank you so much for joining me in this green void, which is actually what Shrek calls his conscience. This year has been hard on him too, guys. A little something about me. I'm joining you today from Chennai, the Detroit of India, and that was not even a joke. You can look it up. When I am not correcting people for pronouncing my name wrong, I work at Grover's and occasionally hunt demons. I also make a lot of memes that prevent me from decimating into the ether, but enough about me. Let's talk about the one thing that Kegel Grandmasters and the Lego Group used to make a fortune. Complicated models. I know Legos are for kids, but if you think that is going to stop me from wasting several months of my life to build the glorious Millennium Falcon, joke's on you, cause I can't be shamed. It's been tried. But yes, today we are going to be talking about some machine learning models. Complicated ones at that. Machine learning has become kind of a buzzword we hear every day, from over-enthusiastic hiring managers to that one coworker who wants to use it for everything. And I mean, of course they do. Machine learning is used everywhere. We are letting data-driven algorithms make a lot of important decisions for us, either directly or indirectly, every single day, sometimes without even realizing it. Some argue that's good, and some think it's getting out of hand. But regardless of whether we like it or not, it's here to stay. Cause from auto-completed ducks to casual racism, spying speakers, and robot dogs, I would say we are very close to realizing that life is just another Black Mirror episode. But let's park the apocalypse talk, cause it's getting too real. Instead, let's take a step back. The concepts and fundamentals of machine learning are like Monty Python movies. By that I mean old. Don't get me wrong, the jokes are still funny, but let's dial down the references a bit. So, moving on. Normally, when you have y is equal to f of x, which is an arbitrary function, or for ease, let's say y equals x squared. So we are given x and told to calculate y. Easy peasy. So when x equals 2, y equals 4. When x is 3, y is 9, and so on. But what if we don't know what y is actually the square of x, and we just know the different combinations of x and y? So now we know 2 it gives 4, we know 3 gives 9, we know 4 gives 16. Now you can ask yourself, what does 5 give? This can go down two ways. Either you have a big brain moment and you immediately spot the pattern and say the answer is 25. And of course you do. You're awesome. Or maybe you have a lot of time in your hands, so you collect more data, you plot it, and you fit the pattern to a curve. Either way, you also want your machine to solve the problem similarly, detect patterns it has already seen, or try to fit the data to conform to a pattern. And since we are not passing it a straightforward function like we usually do, we want whatever algorithm we are using to learn this function from the given data. This is literally what machine learning is. So the theory was all set and ready to go, but the times were not. It's like this scene in the Back to the Future. Machine learning was not ready to be mainstream yet. It took a little bit of time, but it's back now. Even though we had several amazing research papers like Neocognitron, which were proposing amazing ideas that would turn out to be the actual foundation of modern day character recognition and pattern recognition models, the ideas were strong, but we lacked the compute and the data needed to train actual accurate machine learning models. Everything was just theory and some execution. So it was all sunshines and rainbows until the internet happened. So let's give a quick shout out to Tim Berners-Lee. Moving on. With the dawn of the internet and Moore's law doing its thing, compute got a lot cheaper and people were willing to give out personal information for a chance to get that snap streak. And if you don't know what a snap streak is, good for you. But I just want to talk to you for a second there. You have lived a truly fruitful life, and honestly, telegrams were the best, am I right? So, Snapchat is a social media app where you can make yourself look like a dog. And you would ask me, why? And to that I say, why not? So, snap streaks count how many consecutive days two people have been messaging each other. Every day they send a snap, their streak gets longer, and as your streak gets higher, the more you feel validated. But this validation is nothing but a fleeting moment of your brain feeding you serotonin to make you forget how conversations have ceased to have meaning, and the only reason you are online is to look at pictures of funny text and promoting your SoundCloud. But then one day you realize this is all an elaborate ploy employed by $1 million company fighting for your attention. This constant fear of being loomed by surveillance capitalism consumes you every waking moment until your opinions have been swayed so many times by information overload that you don't know what your opinion is anymore. You don't even know if you have opinions anymore. You don't even know if you have the ability to make choices anymore. Well, that's what Snapstreak is, but lit emoji, guys. So, moving on. With the abundance of data pouring in and GPUs becoming more common than brown guys at a tech conference, it became incrementally easier to train complicated machine learning models and get amazing results. Well, not always amazing. Case in point. Let's start with the why. Let's first assume that robot that's going to rehab works based on decisions coming in from a machine learning model. Now, why would my model make bad decisions? Well, there may be a lot of reasons for it. Maybe your code was written in JavaScript and self-destruct was the right call. That was JavaScript roast going off the Python conference bingo. Or maybe you forgot an if condition. But after slowly fixing all the possible bugs and evaluating your algorithm, you start to wonder maybe the issue is not you. Maybe it's the data. And you know what? There are some usual suspects. Here, as Professor McGonagall says, historically we have had problems with these three. And by these three, I mean noise, bias, and variance. So let's go through each one of them. Starting with noise, the essential ingredient of every Zoom call. Noise is when the data you use to build your model is littered with large quantities of additional meaningless information in it, called noise. There are several techniques and methods you can use to reduce noise, like principal component analysis to reduce the dimensions. You can use denoising techniques, you can filter your dataset, and so on. But the most straightforward way is to actually just collect more data. And you know what the elders say, the best way to fight eleki in your biryani is by adding more biryani. And if you don't know what a biryani is, I just feel sorry for you and your taste buds. I don't want to get hungry though, so moving on to bias, a fancy word for opinions that suck. Bias is when the available data is not representative of the population. It's when your model makes these assumptions so that it's easy to learn the target function. And data is not the only thing that suffers from bias. Humans do too. Again, there are several methods and techniques to reduce bias in machine learning. You can try and reduce missing data with imputation techniques. You can also try adjusting the data, which have different scales, by applying feature scaling in order to normalize your dataset. But like the best thing you can do to mitigate bias is to collect more data, and this time around you can try to be more diverse and inclusive. This again holds true for data and humans. Assumptions made about race, gender, and other superficial things in your dataset can have serious real-world implications. Let's take COMPAS, for example, which stands for Correctional Offender Management Profiling for Alternative Sanctions. Oof, let's stick to COMPAS. This was a regression model built to forecast which criminals were more likely to reoffend. COMPAS has been used by the US states of New York, Wisconsin, California, and Florida. On the outside, the model was textbook. It was trained on a dataset based on a survey that asked a bunch of questions. And the model used the answers to those questions as features and optimized for accuracy. Everything was awesome until the model predicted double the number of false positives for recidivism in African American ethnicities than for Caucasian ethnicities, which sucks. If the developers had looked for bias, they would have found it and could have adjusted the model instead of exacerbating the existing issue. So I just wanted to stress on the fact that as developers, we tend to focus so much on the technical aspects that we sometimes forget the human aspects. And the decisions we make have real implications. So just reminding people about that. Moving on to variance. According to ancient scripts on statistics, variance is the expectation of the square deviation of a random variable from its mean. And that's the formula. Yes, that was a 5-mark question and I got it right. Off the record, variance describes how much a random variable differs from its expected value. It's kind of like the word serverless. You first hear it and you think about it and you think, man, did they finally manage to get rid of servers? But in reality, serverless is something we made up to sound clever. Variance is kind of like that. It shows how much expectations can hurt you. Let's actually dig deeper into variance. Let's assume you want your algorithm or your machine learning model to learn a pattern. So you give your model this sequence. It's just a bunch of even numbers, right? So your model is happy because it saw the pattern right away. Your algorithm is all like, okay, this is nice, looks neat, I can handle it, but now let's take the training wheels off and pass it 13. Now the model is confused. It was so sure that the patterns were going to fit exactly that it now tries really hard to somehow fit 13 into the given pattern, which might land us in a whole world of trouble, especially when 13 is an outlier or noise in the data. Maybe the next number in the sequence is 14 and things go smoothly thereafter. We just don't know. And that is the problem with high variance. Variance is essentially your model's sensitivity to fluctuations in training data. And having high variance can cause an algorithm to model random noise in the training data rather than the intended output. There is an interesting inverse relationship between bias and variance, because the more you are biased towards something, the less you're going to be affected by changes to it. This leads us to the famous bias-variance trade-off. And what we want to do is hit that sweet spot. Machine learning models are really affected by bias-variance trade-off. Sometimes they have high variance, which means they don't generalize. Which means they might give you excellent performance on training data, but when it comes to real life, they fail spectacularly. We call this overfitting, whereas models with high bias kinda oversimplifies the model and underfits, which makes both these models weak. So, what do we do with these weak models? Well, these weak models band up with several other weak models and become something strong enough to take over the human race. We all love a good underdog story, don't we? So when these weak learners or base models are combined, we get something exquisite, like Big Chungus, Handsome Squidward, or Adam Driver. Perfect. Combining results from weak learners actually brings us to the main topic, ensembling models. Ensembling models are basically ensemble is a fancy word for combine. So it's when we combine two or more algorithms or models that could improve or boost your accuracy. Ensembling models are kinda like developers who want to learn Rust. They are everywhere. Ensembling models are common goods on Kaggle. They actually win a lot of competitions. And for a reason. But there is a method to the madness. You cannot just randomly combine results from two models and pray to God it works. It's math, not Jamba Juice. But there are some really well-defined strategies you can use to ensemble models, and we are going to unpack those strategies. So, suppose we have a model that's low on bias and high on variance. This means we need to combine it with a model that tends to reduce variance. Similarly, if a model has high bias and low variance, we need to combine it with a model that would decrease bias. It's kind of like mixology, but for nerds. Now that we know what to do, let's talk about the ways we can do it. Bagging, boosting, and stacking. If you're hearing these for the first time, they might sound like strategies you use during Black Friday. We are bagging and then we are boosting this, and stacking, oh, we are definitely stacking. Bagging aims to reduce variance, whereas boosting and stacking focus on reducing bias. I just threw some words at you there, but don't worry, it's my duty as a brown guy on the internet to explain it to you. Let's start with bagging. Bragging without the R. No, bagging actually means bootstrap aggregation. Bootstrapping is a statistical method that resamples a single dataset to create many simulated samples. Now, we fit these smaller, weaker models independently on these bootstrap samples. After fitting, we aggregate the results from these samples to create an averaged output. This way, we generalize, reduce overfitting, and hence the variance. This is essentially what bagging models do. And also, since we train models independently, there is a possibility of parallelization. And you know what they say about parallelization? I actually don't know. It's been so long since I went out, I cannot remember what people say about things anymore. But enough about me. Let's talk about random forest. Random forest is a really popular bagging method where, along with bootstrapping data, we also sample over the features and keep only a random subset of them to build a tree that in turn makes a forest. Sampling over features means that all the trees do not look exactly the same, look at the exact same information to make their decision, and so it reduces correlation between the different results returned, which, guys, is an amazing way to generalize. It becomes quite easy to measure the relative performance of each feature on the prediction. By looking at the feature importance, you can also decide which features to possibly drop because they don't contribute enough, or sometimes nothing at all, to the prediction process. This is important because the more features you have, the more likely your model will suffer from overfitting. Random forest can be used in both classification and regression problems. Also, another added advantage of feature sampling is that now a model can handle missing data quite well. On to our next method, boosting. A method that's so overused, that's it, there is no punchline. Bagging was like the Fast and Furious movies. There are a lot of them, and they do almost always have bald men and objectification. And boosting is like the Lord of the Rings trilogy, each one building on the glory of the previous one. I mean, that's how you do a trilogy. What I mean to say is that bagging was a parallel technique while boosting is sequential, where each model in the sequence is fitted, giving more importance to observations by the previous model in the sequence, which means each predictor tries to correct its predecessor. So the model iteratively improves itself. I hope my PM is watching this because he sure loves those iterations. In the end, we get a model with low bias and sometimes even low variance, which is awesome. But as always, sequential evaluation comes with its perils, especially when we are fitting expensive models in a sequence. But there are still questions like, how do we aggregate models and what information do we carry forward from the previous model to iteratively improve? What I mean to say is that boosting is based. But based on what? Let's find out. Weight-based boosting. Suppose you have a training model where every predicted label is assigned a weight, depending on the prediction. Good prediction mean less weight, and bad prediction mean more weight. It's kind of like karma, but without the constant fear of eternal damnation. These weights get added up at every model in the ensemble, and as more weights get added to a label, you understand that you need to get better at predicting it, and you start to focus your model on them instead of those with lower weights. This goes on until a threshold is reached, like maximum accuracy or max number of models. An example of this is adaptive boosting or AdaBoost. AdaBoost was designed in such a way that at every single step, the training data is adapted to assign more weights to misclassified samples and less weights to correctly classified samples. And the final prediction is a weighted average of all the final predictions or weak learners, where weight is placed on strong learners. AdaBoost is really good at classification problems. So this is weight-based boosting. Next up, we have residual boosting, aka gradient boosting, aka the breadwinner. In this type of boosting, we sequentially try to correct the error of the previous model the same way, but instead of tweaking the weights, we take the residual errors of the predecessor as a label for the next model. So if the actual value is 1 and the predicted value is 0.75, then we take the residual error, which in this case, let's assume is the difference. So we take 0.25 as a label to the next model for prediction. So we just plug in a loss function like gradient descent. Exactly, which is why this method is also called gradient boosting. But here the gradient refers to finite differences instead of a derivative. Another important feature of gradient boosting is shrinkage. It's a simple strategy to reduce overfitting by scaling the contribution of each weak learner by a factor of a parameter, also called its learning rate. This means that if learning rate is low, we need a large number of weak learners to compensate. Just like AdaBoost, in the end it is also the weighted sum of weak learners, but while adaptive boosting tries to solve at each iteration a local optimization problem, by which I mean it tries to find the best weak learner and its coefficient to add to a strong learner, gradient boosting depends on a gradient descent based approach and can be more easily adapted to a large number of loss functions, so it's more flexible. Looking at it like this, we can see that AdaBoost is essentially nothing but a special case of gradient boosting where we are iteratively minimizing one subproblem at a time. A really popular version of gradient boosting is XGBoost or extreme gradient boosting. This method successfully employs gradient descent, a gradient boosting with a little tweaks of its own. It's also distributed, hence fast, highly effective, and tractable for big data sets. This model is kind of like the cool kid in the circle that everyone wants to do nice with, and it's also extreme. Well, end of the day, the main difference between bagging and boosting is that in bagging we work on individual models parallelly, where in boosting each model's performance affects the next model, and in both models we use voting and combine the models of the same type. But what if? Hear me out. What if we combine results from different models? No. But what if? Nah. Unless there is another method in ensembling. There's another ensembling method called stacking, where a new model learns how to best combine predictions from multiple existing models. Now, how would that happen? Well, in stacking, predictions are first generated using various machine learning algorithms. These are then used as inputs to a second level algorithm. This algorithm is trained to optimally combine predictions from multiple models to form a new set of predictions. The base models can be anything from a simple regression model to a complex multi-layer perceptron. And it's not always just two levels. We can stack multiple models and create increasingly complex ensembles to beef up our predictions. Stacking models is kind of like stacking weights at the gym. The more you stack, the more attention you get. And when you stack well and train harder, you can hit that goal. And you could ask me, with this body, is there any way I could be training any harder? And you are right, I'm a beast. Not a day goes by that I don't sacrifice sweat to the gods of swole at the Temple of Iron. I didn't move to Meat Street yesterday. I got a mortgage from Wells Fargo and I have been passing plates ever since. I call this one papier and this one mache because I am shredded. Moving on. Ensembling models are in no way the silver bullet. It's not even a bullet, it's a combination of existing bullets. So it's more like a shotgun. And you know what? Shotguns are used only in the middle of a zombie apocalypse. Everyone knows that. Sometimes your data just fits in a line or a curve, and ensembling models are overkill for most of these problems. And now it's kind of become a competition. Who wants to build the most complicated stacking model? And you can see this all over the internet. People trying to outstack each other, spending tons of compute and GPU for a 0.2% increase in accuracy. This makes sense when you want to win a competition, but in the real world, you also want to be practical. Which brings us to the Achilles heel of ensembling models. Ensembling models, as I said a lot of times, are complicated, which means they are hard to explain or even interpret. And a lot of the times, interpretability is really important. A slightly low-performing explainable algorithm is sometimes way better than an accurate black box. Black box models are like heuristic techniques. They don't actually mean anything unless you understand what's exactly happening. A quick side note, just an idea. Hear me out, because I have two words for you. Serverless heuristic. Huh? I will let you sit on that. In the meantime, let's discuss techniques you can employ to interpret a black box model. Let's start with LIME, which spells out as Local Interpretable Model Agnostic Explanations. We like to shorten these things to sound clever. LIME tries to learn the behavior of the underlying model by changing the input and see how the predictions change. So, what we try to do is to generate an explanation by approximating the underlying model, which is complex and probably non-linear, locally with an interpretable one like a linear model. And even if you replace the underlying machine learning model, you can still use the same local interpretable model for explanation, which is why it's model agnostic. LIME is also one of the few methods that works for tabular data, text, and images. But also, LIME has a really big problem with instability in its explanations. For example, if you repeat the sampling process for the dataset and rerun LIME, then the explanations that come out can be widely different. And instability means that it's difficult to trust the explanations, and you should be very critical of it. There's also this other technique we can employ, which is actually based on game theory. So to do that, let's define a game, which is how many bugs in the code. So the gain from the game is going to be the actual prediction minus the average prediction. So in this case, the actual prediction is 62 and the average is 20. So the gain is 42, which is also the answer to life, the universe, and everything. Now let's look at the players that contribute to this score. Stack Overflow is a player which rightly contributes 100 points to the gain. Next up, we have luck. Maybe you are coding on a full moon day and the power is with you, so it contributes 50 points to the score. And the last player in this game is the programming language, which let's say is JavaScript. So you lose 108 points. So this means the gain you are left with is 42. I would know, I tweaked the numbers. But this is essentially the concept of Shapley values. The method called SHAP or Shapley additive explanation tries to explain the prediction of an instance X by computing the contribution of each feature to the prediction. It does that by calculating the Shapley values that we discussed. If feature values are players in a game with predictions as the payout, then Shapley values, they just tell us how to fairly distribute the payout among the features. I understand I just merely scratched the surface with a really shallow explanation, but you know what? There are a lot of cool things to explore in this realm. And if you want to know more, actually showed this slide before accidentally, but I would actually highly stress that you actually check out this book because it is amazing. It's Interpretable Machine Learning by Christopher Molnar. I can go on talking about building complicated ensemble models, but it would not help a lot until you understand the why. And I mean the problem that you're trying to solve. And after we fully understand the extent of our problem, then we can do whatever we want. We essentially end up on Minecraft creative mode. Now, this talk is officially a burrito because I'm going to wrap it up. I just want to take a moment to thank Pi Gotham and each and every one of you watching for tolerating me and my questionable jokes. Also, this is the first time I'm trying out something like this, so I would love to hear what you think. So please join me in the endless circle of social validation, because I sure would love that social currency induced dopamine hit. Again, thank you for being here. I will see you around. Okay, bye.